Welcome to the calm unknown. Tonight, we explore a quiet mystery that shapes how we see the world. The universe is vast, and much of it remains hidden, not because it isn't there, but because it's just beyond what we understand. Let's begin. Imagine standing alone on a quiet night, far from city lights, looking up at a faint river of light stretching across the sky. For thousands of years, that pale band has watched over humanity, guiding travelers, inspiring myths, whispering of something beyond our reach. Yet it has never truly shown its face. You are looking at the Milky Way, your home galaxy. But you are also looking from inside it, like a fish trying to describe the ocean while swimming through it. We are embedded so deeply in the galaxy that seeing its full shape has always been nearly impossible. The greatest obstacle is dust, thin veils of microscopic grains born from dying stars drift through the disk where most stars live. These clouds block visible light almost completely beyond a few thousand light years. In the direction of the galactic center, the dust is so thick that it swallows nearly all starlight. What reaches us is only scattered hints. A glow here, a dark rift there, turning the galaxy into a foggy labyrinth. Centuries ago, astronomers tried to map this hidden giant using only what they could see. William Herschel, in the late 1700s, patiently counted stars in hundreds of directions. He concluded we lived near the center of a flattened, roughly symmetrical system. It was a brave attempt, but wrong. The dust had fooled him. The center was much farther away, hidden behind the darkest lanes. It took until the early 1900s for the truth to begin emerging. Harlow Shapley studied globular star clusters, ancient spherical swarms that orbit far outside the dusty disk. Because they were visible in all directions, he could use them as distance markers. His measurements revealed something startling. The clusters were not centered on the sun. Instead, they clustered toward a distant point in the constellation Sagittarius. The sun and Earth were far out in the suburbs, roughly 26,000 light-years from the true center. Each new tool peeled back another thin layer. Radio waves, discovered in the 1930s, could pass through dust where light could not. Suddenly, we heard the hiss of hydrogen gas tracing spiral arms. Infrared telescopes in the late 20th and early 21st centuries saw the warm glow of obscured stars. Bit by bit, the picture sharpened. We live in a barred spiral galaxy, with a bright central bar and sweeping arms, yet even these views remain incomplete. Dust still absorbs or scatters much of the light. Many regions remain stubbornly dark. Why does the galaxy guard some areas more fiercely than others? What lies behind the next curtain? Today, the Gaia spacecraft is conducting the most ambitious census ever attempted, measuring positions, motions, and distances for over 2 billion stars. With each data release, the map grows clearer. Hidden patterns are beginning to surface, waves in the disk, ancient merger scars, vast bubbles of hot gas. We are on the verge of seeing structures we never suspected existed. But we are not quite there yet. The galaxy still breathes slowly, patiently, holding most of its architecture just out of reach. You live inside a galaxy that has successfully hidden most of its architecture from you for your entire life. And it is still hiding things today. Now that we can finally trace the broad outline of our home, let us step back and take in the shape that has emerged. Picture a vast, living pinwheel, slowly turning, breathing in gas, breathing out stars. At its heart lies a bright bulge, swollen with ancient suns. Extending from that bulge is a long central bar, a hidden backbone only confirmed in the early 2000s. This bar acts like a quiet conductor, funneling fresh gas inward and helping maintain the graceful sweep of the spiral arms. The arms themselves are not solid structures, but gentle density waves, rivers where gas compresses, cools, and ignites new stars. Over billions of years, you might expect those arms to wind up tightly, like cream stirred into coffee. Yet they remain open and well-defined. Something keeps them from tangling, perhaps the bar, perhaps passing satellite galaxies, perhaps processes we do not yet fully grasp. Surrounding the bright disk is a faint, spherical halo, an enormous envelope of old stars, globular clusters, and invisible dark matter. The disk itself has layers, a thin disk where most young stars reside, and a thicker, older layer of stars that puff upward and downward like embers rising from a dying fire. These layers are memories, traces of the galaxy's violent youth, its mergers, its slow settling into maturity. Our sun sits almost precisely between two major spiral arms, the Sagittarius arm inward, the Perseus arm outward, in a quieter interarm region sometimes called the Orion Spur. This placement may have been crucial. In the dense, star-forming arms, frequent supernovae and intense radiation might have made stable planetary systems rare. Here, in relative calm, life had room to emerge and persist. But that same quiet location also blinds us to the galaxy's more dramatic regions. We see the arms edge on, their beauty and chaos partly concealed. The entire structure rotates with majestic slowness. The sun takes roughly 220 million years to complete one orbit around the center, a cosmic year. Stars closer in move faster. Those farther out drift more leisurely. This differential rotation should have sheared the disk into chaos long ago, yet pattern and order persist. Modern maps, built from infrared surveys, radio observations, and Gaia's precise measurements, reveal a galaxy roughly 100,000 to 150,000 light-years across, containing 200 to 400 billion stars. Yet beneath this apparent order lie irregularities that refuse to fit any tidy blueprint. Gentle waves ripple through the disk. Ancient streams of stars drift like ghost rivers. Enormous bubbles loom above and below the plane. We finally mapped the grand design of our galaxy and discovered it does not quite match any blueprint we expected. At the very heart of this grand design sits something that casts a shadow over everything else, a quiet monster that may have shaped many of the mysteries we are about to meet. Let us now journey inward, toward the crowded, hidden core. The galactic center lies 26,000 light-years away, behind the thickest walls of dust. Moving in that direction feels like leaving quiet suburbs for a violent metropolis. Star density rises dramatically. Gas clouds collide. Massive stars burn briefly and brightly. At the exact center waits Sagittarius A, a supermassive black hole 4 million times more massive than the Sun. Yet it is strangely quiet. Most of its counterparts in other galaxies blaze with the light of infalling matter. Here, only occasional flickers betray its presence. In 2022, the Event Horizon Telescope delivered humanity's first direct image, a glowing orange ring surrounding a dark shadow. That shadow is the event horizon itself, the boundary beyond which light cannot escape. For the first time, we photographed the edge of nothingness. Stars near this invisible point move at staggering speeds. The star S2, on a 16-year orbit, reaches over 3% the speed of light at closest approach. Its path traces a perfect rosette around the unseen mass, one of the strongest confirmations of general relativity in the universe. Yet the black hole appears underfed. Vast reservoirs of gas surround it, but little falls in. Why so calm when it should be feasting? Some suggest past activity cleared the inner regions. Others propose magnetic fields hold material at bay. A few even wonder if feedback from star formation nearby plays a role. Around the black hole swirls a chaotic mini-spiral of warm gas and dust. Magnetic fields twist into towering filaments. Hot plasma bubbles outward. Young, massive stars cluster in groups that should have been disrupted long ago. This central region is both beautiful and terrifying. A place where gravity rules absolutely, yet somehow maintains an uneasy equilibrium. At the center of everything we know lies a place so dense that light itself cannot escape. Yet it is strangely, almost suspiciously, quiet. We have visited the forbidden core and survived, but the whispers remain. Why the quiet? What past outbursts shaped the surrounding chaos? And what strange structures rise from this violent heart into the wider galaxy? As we pull back from the black hole's doorstep, something enormous begins to rise above and below the galactic plane. Structures so vast they dwarf entire star clusters, yet almost invisible until a chance discovery in gamma rays. We have stepped back from the black hole's doorstep, from the crowded violence of the galactic center. Now, something else demands our attention. Something far larger, far quieter, and far more astonishing. In 2010, astronomers working with data from the Fermi Gamma Ray Space Telescope noticed something strange. After carefully subtracting all known sources of high-energy light, two enormous symmetrical lobes remained. They extended above and below the galactic plane like ghostly balloons, each stretching more than 25,000 light-years from the center, half the height of the entire visible Milky Way. They were completely invisible in ordinary light. Dust hid them. Stars did not trace them. Only the highest energy gamma rays revealed their outlines, sharp, almost artificial edges glowing against the darkness. These are the Fermi bubbles. Imagine them, two vast cavities, perfectly mirrored across the disk, inflated from the heart of the galaxy like silent trumpets announcing an event long past. Their combined volume is staggering, large enough to swallow thousands of smaller galaxies whole. Yet for decades they sat hidden in the data, unnoticed, waiting for the right eyes to see them. The discovery was accidental. Scientists were mapping known cosmic ray interactions when the subtraction left these giant silhouettes behind. No model had predicted them. No earlier telescope had possessed both the sensitivity and the wide field of view to catch them. Their surfaces shine in gamma rays produced by particles accelerated to nearly the speed of light. These particles crash into rarer gas within the bubbles, producing the glow we detect. But the edges are remarkably crisp, not the soft diffusion you would expect from gradual leakage, but boundaries that suggest a sudden, powerful event. How long ago did this happen? Estimates range from a few million to perhaps 10 million years, recent in cosmic terms. The black hole may have briefly awakened, swallowing a large cloud of gas, and then exhaling enormous jets that punched through the disk and inflated these cavities. Or perhaps a burst of star formation near the center produced thousands of supernovae in rapid succession, their combined winds driving the expansion. Whatever the cause, the energy required is almost incomprehensible, equivalent to millions of supernova explosions released in a relatively short span. Stand beneath a dark sky and look toward the center. You see only the familiar band of the Milky Way. But high above and below that band, invisible to your eyes, these colossal structures rise like silent guardians, remnants of an outburst that shook the galaxy yet left barely a whisper in visible light. Two invisible structures, each larger than many galaxies, rise from our center like silent trumpets, and we only noticed them 15 years ago. Scientists soon realized these bubbles were not empty. Something had filled them with unimaginable energy. But when and how? The Fermi bubbles are not hollow. They contain hot plasma at millions of degrees, threaded with magnetic fields and populated by cosmic rays, the fastest particles in the universe. But two main stories compete to explain their birth. The first points back to Sagittarius A. Most supermassive black holes in other galaxies shine brilliantly as matter spirals in, heating to incandescence before crossing the event horizon. Our own black hole is dim today, but it may not always have been so quiet. A few million years ago, it might have captured a large gas cloud, or even a disrupted star cluster. As material fell inward, powerful jets shot out along the black hole's spin axis, twin beams of energy punching perpendicular to the disk, carving out the bubbles and heating the gas within. This idea fits the symmetry beautifully. The bubbles align almost perfectly with the galactic center, centered on the black hole's position. Their sharp edges suggest a rapid, explosive phase rather than gradual buildup. The second story shifts the blame to stars. The central molecular zone surrounding the black hole is packed with dense gas. In the past, that gas may have collapsed into an intense burst of star formation, thousands of massive stars born almost simultaneously. These stars live briefly and die violently. Their supernovae and powerful winds could have acted in concert, driving a super wind outward that inflated the bubbles over time. This stellar scenario appeals because we see evidence of recent star formation near the center, and the energy budget roughly matches. Yet it struggles to explain the perfect symmetry and the bubble's alignment with the black hole. New observations have complicated both tales. In recent years, X-ray telescopes like Rosetta have mapped the bubble's hotter interiors, revealing edges that match the gamma-ray boundaries almost exactly. Microwave haze detected by Planck adds another layer, a subtle fog of emission that follows the same shape. And then there are the cold gas clouds. Deep within the million-degree plasma, astronomers have found dense, cold clouds surviving where they should have been vaporized instantly. Some of these clouds are even falling back toward the disk at high speed. Ice cubes in a furnace that somehow endure. Their presence hints at complex cooling processes, or perhaps continuous replenishment from the disk. As of early 2026, the debate remains open. Improved Fermi data and new analyses slightly favor a past black hole outburst, but stellar feedback cannot be ruled out. Perhaps both played roles. A Seyfert-like flare from Sagittarius A, combined with sustained stellar activity. Whatever the truth, the bubbles remind us how dynamic our galaxy still is. An event powerful enough to reshape half its height occurred in the cosmic blink of an eye, and we are only now piecing together the echoes. Something once released enough energy to inflate structures the size of the Milky Way's height. But was it the black hole waking up? Or an army of dying stars? As we study the bubble's edges, another mystery glows faintly in the very center, an excess of gamma rays that refuses to match any known source. Before leaving the bubbles entirely, let us linger on one final puzzle they frame. The same Fermi telescope that revealed the giant lobes also detected a softer, more diffuse glow concentrated toward the inner galaxy. This gamma-ray excess peaks at the center, but extends outward in a roughly spherical pattern, distinct from the sharper bubbles, yet occupying the same crowded region. Known sources, cosmic rays hitting gas, pulsars, supernova remnants, have been carefully modeled and subtracted. Yet a stubborn surplus remains. Its spectrum and distribution match remarkably well with what we would expect if dark matter particles, scattered throughout the halo, were gently annihilating one another near the dense center. But that is only one possibility. Another growing explanation suggests thousands of millisecond pulsars, ancient, rapidly spinning neutron stars, whose combined faint beams could mimic the signal perfectly. The debate has continued for over 15 years, sharpened by each new data release. Recent 2025 analyses using improved instrument calibration show the excess slightly softer at higher energies than pure dark matter annihilation would predict, tilting the balance toward pulsars for now. Yet the spatial pattern remains stubbornly bulbous, more symmetrical than the known stellar distribution. Whichever explanation ultimately wins, the central glow sits nestled within the larger story of the bubbles. If the black hole once flared dramatically, it might have injected both the cosmic rays that power the bubbles and the conditions that shaped the excess. If stellar activity dominated, the same supernova could have produced both the superwind and a rich population of pulsars. The glow may fade or sharpen with the next telescope, but right beside it stand threads of plasma that have puzzled us even longer. Rising like rigid bristles from the galactic plane, these filaments stretch for dozens of light years, defying every gentle rule of cosmic gas. We have lingered near the colossal Fermi bubbles and the strange threads that rise beside them. But before we move onward, let us return once more to the very heart of the galaxy, to a subtler mystery that has haunted astronomers for over 15 years. In the same data that revealed the bubbles, another signal hides in plain sight. It is not sharp-edged or dramatic. It is a gentle, diffuse glow of gamma rays, the highest energy light in the universe, concentrated toward the inner few thousand light-years. This glow peaks brightly at the center, then fades gradually outward in a roughly spherical shape, extending well beyond the dense stellar bulge. Astronomers call it the galactic center gamma ray excess. To find it, researchers must perform an intricate subtraction. They model every known source, cosmic rays slamming into interstellar gas, supernova remnants, pulsars, even the inverse Compton scattering, where starlight is boosted to gamma energies by fast particles. Layer by layer, these contributions are removed. What remains is a stubborn surplus, a soft, persistent light that refuses to vanish. Its spectrum, the distribution of energies, is distinctive. A broad peak around a few billion electron volts, falling off gently on both sides. Its spatial pattern is almost perfectly centered on Sagittarius A, more bulbous and rounded than the flattened distribution of ordinary stars or gas. For many years, this excess has carried a tantalizing possibility. Dark matter, the invisible substance that outweighs ordinary matter 5-to-1 across the universe, is thought to consist of particles that rarely interact with light or normal matter. In the dense inner galaxy, where dark matter should concentrate strongly, these particles might occasionally meet and annihilate, converting their mass into pure energy in the form of gamma rays. The observed excess matches many dark matter models remarkably well. The energy spectrum aligns with what theorists expect from particles in the 30 to 60 GeV mass range. The spherical distribution fits the predicted dark matter profile far better than the disk-like pattern of ordinary sources. Yet the story is far from settled. Right at the heart of our galaxy shines a light no known object fully explains, and some believe it could be the fingerprint of dark matter itself. The dark matter interpretation excites many because it would offer a direct glimpse of physics beyond the standard model. But alternative, more mundane explanations have gained strength in recent years, and as data improves, the picture grows ever more nuanced. The leading conventional explanation points not to exotic particles, but to a hidden population of dead stars. Millisecond pulsars are neutron stars that have been spun up to extraordinary speeds, rotating hundreds of times per second, by stealing matter from companion stars in their youth. Today, they tick like precise cosmic clocks, their powerful magnetic fields accelerating particles that emit beams of radio waves and gamma rays. Individually, these objects are faint in gamma rays, but thousands of them, scattered throughout the inner galaxy, could collectively produce a smooth, extended signal that mimics the excess almost perfectly. Evidence for this idea has grown steadily. Deep radio surveys with telescopes like Meerkat have uncovered more and more millisecond pulsars in the central region, dozens so far, with hints of hundreds or thousands still unresolved against the bright background. Their combined luminosity, if scaled up, comes remarkably close to the observed excess. Recent studies, including analyses released in 2024 and 2025 using refined Fermi-Lat data, show subtle mismatches with simple dark matter models. The excess appears slightly softer at higher energies than pure annihilation would predict. Its morphology, while bulbous, shows faint extensions that align better with the known distribution of old stars than with some dark matter profiles. Yet the pulsar explanation has its own challenges. The spatial pattern remains almost too symmetrical, too centered on the black hole. Millisecond pulsars should trace the stellar bulge, which is slightly flattened and offset, and we have not yet detected nearly enough individual sources to account for the full brightness, though many may simply be too faint or confused with background emission. A twist arrived in late 2025 analyses. The excess seems to vary slightly in intensity over time, more than expected for steady dark matter annihilation, but consistent with a population of variable pulsars. Still, other studies argue the variability is marginal within statistical uncertainty. The debate is not a simple either-or. Hybrid scenarios exist. A weaker dark matter signal overlaid on a dominant pulsar population, or unresolved point sources of other kinds. New instruments, from the upcoming Cherenkov telescope array to improved Fermi calibrations, promise to resolve fainter sources and map the spectrum with greater precision. Thousands of dead stars could be blinking in unison right where we see the mysterious glow. But their pattern is almost too perfect. Whichever way the evidence tips, the excess forces us to confront how much remains hidden in the crowded inner galaxy, whether invisible particles or overlooked stellar remnants. As we weigh these competing tales, one truth emerges clearly. The galactic center is far more complex than any single explanation can capture. Both dark matter annihilation and a rich pulsar population would imply vast hidden ecosystems operating quietly for billions of years. Dark matter would reveal the gravitational scaffolding that shaped the galaxy from its earliest moments. Pulsars would speak of generations of binary stars, disruptions and recyclings in the dense core. Recent multi-wavelength studies have added new layers. X-ray observations with Chandra and New Star show faint point sources that could be unresolved pulsars or other high-energy objects. Infrared surveys with the James Webb Space Telescope, peering through dust, reveal stellar densities and dynamics that refine our models of source distributions. The excess does not stand alone. It overlaps spatially with the Fermi bubbles, the radio filaments, the central molecular zone. If the black hole once flared, it might have injected cosmic rays that contribute to the glow. If stellar feedback dominates, the same supernovae that drove the bubbles could have left behind a pulsar-rich aftermath. As of early 22R6, the balance tilts slightly toward pulsars, but the door remains open for a dark matter contribution, perhaps a subdominant signal that future instruments will isolate. Either outcome would be profound, confirmation of new physics or proof of an entirely overlooked stellar population in our own backyard. The glow may fade or sharpen with the next telescope, but right beside it stand threads of plasma that have puzzled us even longer. Rising like rigid bristles from the galactic plane, these filaments stretch for dozens of light years, defying every gentle rule of cosmic gas. We have weighed the faint central glow and its competing explanations. Now let us turn to structures that stand in stark contrast, not soft and diffuse, but strikingly rigid and organized. Within a few hundred light-years of the galactic center, scattered among the chaos of gas and young stars, rise long, narrow threads visible only in radio waves. Discovered in the 1980s by radio astronomers scanning the heart of the Milky Way, these non-thermal filaments appear as perfectly straight strands against the turbulent background. Some stretch more than 100 light-years in length, yet remain only a few light-years wide, extraordinarily slender for cosmic structures. They stand almost vertical to the galactic plane, like rigid bristles rising from a brush. What makes them so puzzling is their straightness. In the violent central region, gas clouds collide, magnetic fields twist, supernova shocks ripple outward. Ordinary plasma should bend, diffuse, or fragment under such forces. Yet these filaments remain remarkably linear, as if held taut by invisible cords. Their emission comes from synchrotron radiation, electrons spiraling at nearly light speed along powerful magnetic fields. The fields within the threads reach strengths far greater than the galactic average, enough to resist the surrounding turmoil and maintain their shape. Many of the filaments appear to point almost directly toward Sagittarius R. Their bases seem anchored in the inner chaos, extending outward like accusing fingers aimed at the black hole. Some pierce through dense molecular clouds without deviation. Others run parallel to one another in small bundles, creating the impression of an organized array. No other region of the galaxy hosts such concentrated, well-ordered examples. A few shorter, fainter filaments have been found elsewhere, but the central ones remain the most extreme. The longest, the straightest, the most numerous. In the wild heart of the galaxy stand perfectly straight threads of magnetized plasma, some reaching toward the black hole like accusing fingers. Scientists have watched these structures for decades, yet their origin remains elusive. Are they illuminated edges of larger magnetic flux tubes, relics of past outflows from the black hole? Or something more widespread that only becomes visible in the center's extreme conditions? The filaments invite many interpretations, none yet definitive. one early idea linked them directly to the black hole. Powerful jets or winds from Sagittarius A, in its more active past, might have channeled magnetic fields outward, lighting up narrow pathways as particles streamed along them. The alignment of many filaments with the center supports this view, as does their polarity. The direction of the magnetic field often runs consistently along their length. Yet the black hole today shows little activity capable of sustaining such structures, and not all filaments point precisely at Sagittarius A. Some run parallel or at slight angles. Another proposal sees them as cosmic strings, hypothetical relics from the early universe, briefly illuminated by passing particles. This exotic idea was largely set aside as observations accumulated. More recent models focus on the galaxy's magnetic field itself. The Milky Way possesses an organized component that runs roughly parallel to the spiral arms, but in the center, turbulence amplifies and stretches field lines. Interactions between orbiting gas clouds and this field could twist it into long, stable tubes. Cosmic rays trapped within then illuminate the tubes in radio light. High-resolution images from the Meerkat telescope in South Africa have revealed exquisite detail. Some filaments gently curve or twist over their length. Others connect to known supernova remnants or molecular outflows. A few appear to transport energy from the disk upward, perhaps helping drive the larger Fermi bubbles. Intriguingly, solitary filaments have now been found far from the center, in the spiral arms and even near the Sun's position. These distant examples are shorter and fainter, but their existence suggests the phenomenon may be galaxy-wide. Local amplification of magnetic fields by turbulence or shocks made visible wherever conditions align. Recent studies propose that the central filaments are simply the most extreme cases of a common process. Supernova remnants, stellar winds, or even the galaxy's differential rotation could stretch and align field lines everywhere. In the dense, energetic center, the effect becomes dramatic enough for us to notice easily. As of early 2026, multi-wavelength observations continue to refine the picture. Very long baseline interferometry now resolves individual threads into finer substructures, showing helical magnetic fields winding along their lengths. Polarization maps reveal how the fields interact with surrounding gas. What if these threads are not unique to the center, but quiet echoes of a galaxy-wide magnetic skeleton we are only beginning to trace? The filaments remind us that magnetism, often overlooked beside gravity and radiation, plays a crucial role in shaping cosmic architecture. They stand as silent evidence of forces that organize chaos into order, even in the galaxy's most violent region. Before we leave the center entirely, one more hidden feature waits in the shadows. An enormous reservoir of cold, dense gas that encircles the black hole like a frozen ring. The central molecular zone extends several hundred light-years around Sagittarius A, containing tens of millions of solar masses of molecular clouds, raw material that could birth millions of new stars. Yet star formation here proceeds at a strangely sluggish pace. In spiral arms farther out, similar clouds collapse readily under their own gravity, igniting clusters of bright, massive stars. Near the center, tidal forces from the deep gravitational well should compress gas even more strongly. Models predict a stellar birth rate 10 or 100 times higher than observed. Instead, much of the gas remains cold and quiescent. Turbulence, stirred by the crowded environment, powerful magnetic fields, or feedback from the scattered stars that do form, all may conspire to inhibit collapse. Cosmic rays streaming from the black hole or past activity could heat cloud surfaces just enough to stabilize them. This frozen nursery adds another layer to the central mysteries. The same region that hosts violent filaments and possible past outbursts also guards vast reserves of future potential, waiting for a trigger we do not yet understand. Surrounding the black hole lies a frozen nursery, billions of solar masses of cold gas, waiting for a trigger we cannot yet name. The center, for all its extremes, maintains a delicate balance: outburst and calm, order and chaos, creation delayed. These intertwined features, bubbles, glow, threads, clouds, paint a picture of a heart that beats slowly, remembering ancient violence while preparing for what may come. While the center guards its secrets fiercely, a completely different kind of hidden structure has been found much closer to home, one that ripples right through our neighborhood. While the center guards its secrets fiercely, a completely different kind of hidden structure has been found much closer to home, one that ripples right through our neighborhood. Pull back from the violent core, past the bar and the inner arms, until you reach the quiet region where the sun drifts. Here, in what we long believed was a calm, flat section of a spiral arm, a vast undulation has revealed itself. In 2019 and 2020, astronomers combined Gaia's precise stellar distances with three-dimensional maps of interstellar dust. What emerged was astonishing: a long, sinusoidal wave of gas and young stars stretching nearly 9,000 light-years along the local arm. They named it the Radcliffe Wave, after the institute where the discovery took shape. Picture it as a gentle ocean swell, frozen in slow motion. The structure rises and falls hundreds of light-years above and below the galactic midplane, like a cosmic serpent coiled through our immediate surroundings. Famous star-forming regions, Orion, Perseus, Cygnus, Scorpius, Centaurus, are not scattered randomly. They sit along the crests and troughs of this single, coherent wave. For decades, two-dimensional maps had flattened the galaxy into a thin pancake. Vertical motions were known, but seemed minor, chaotic. No one suspected such an enormous, organized oscillation hidden in plain sight. The sun itself sits near a crest, roughly 500 light-years above the average plane. We live on the upward slope of this vast ripple, looking slightly downward toward the center. Below us, the wave dips. Above, it climbs toward distant nurseries where new stars ignite. The mass involved is staggering. Millions of times the sun's mass in gas, and young stars, all moving together with remarkable coherence. The wave oscillates vertically at speeds of several kilometers per second, yet its length and amplitude have persisted for tens of millions of years. How can something so massive remain so ordered? Gravity should have damped such motions long ago, pulling everything back toward the flat disk. Yet the Radcliffe wave endures, almost as if the initial disturbance happened recently in cosmic terms. The spiral arm we live in is not flat and calm. It undulates up and down like a cosmic serpent stretching across thousands of light years. Stand under a dark sky tonight. The bright patches of Orion and Scorpius lie along this hidden wave. The stars you see are not merely scattered. They trace a vast breathing structure that cradles our entire neighborhood. And it was only in the last few years that we finally saw its true shape. What could have struck the disk hard enough to set this wave in motion? And are we seeing the scars of ancient impacts all around us? The Radcliffe wave did not form gently. Something delivered a powerful kick to the galactic disk tens of millions of years ago, and the ripple from that impact still travels through our region. Several suspects have emerged. The leading candidate is a close encounter with a satellite galaxy. The Sagittarius dwarf spheroidal galaxy, a small companion now being torn apart by the Milky Way, has plunged through the disk multiple times in the past. Simulations show that such passages can excite large vertical waves, bending the disk like a drumhead struck off center. The timing matches roughly. One of Sagittarius's earlier crossings, perhaps 50 to 100 million years ago, could have launched the disturbance we see today. Yet the fit is not perfect. The wave's orientation and amplitude require a specific angle and speed of impact. Recent modeling, as of 2025, suggests the Sagittarius dwarf alone may not explain the full coherence. Additional perturbations might be needed. Another possibility points to dark matter. The Milky Way's halo should contain thousands of smaller dark matter subhalos, invisible clumps left over from the galaxy's formation. If a massive subhalo, perhaps several million solar masses, passed through the disk near our position, its gravity could have tugged stars and gas upward and downward without leaving visible traces. Such events would be rare, but plausible, and they naturally produce long, linear waves. Some studies favor a more distant trigger, pressure waves from the central black hole's past outbursts. The same activity that may have inflated the Fermi bubbles could have sent shock fronts racing outward, compressing gas and exciting oscillations far from the center. Though weakened by distance, such waves might still imprint vertical motions in the outer disk. Recent analyses, incorporating Gaia's later data releases through 2025, have added intrigue. The Radcliffe wave appears dynamic, not a static fossil, but still oscillating. Vertical velocities remain coherent along its length, suggesting damping has been slower than expected. Magnetic fields threading the gas may act like tension in a string, helping preserve the wave's shape. Or ongoing minor disturbances, smaller satellite passages or internal instabilities, could be feeding energy back in. Whatever the cause, The wave reminds us that the galactic disk is alive, responsive. It records impacts like tree rings record seasons. Our quiet neighborhood bears the subtle scar of a violent graze long ago. Something massive grazed our part of the galaxy tens of millions of years ago, and the ripple is still traveling. The sun and its planets formed near the crest of this moving wave. Perhaps that position influenced the distribution of material in our early solar system. Perhaps it even affected the stability of orbits in the outer clouds where comets dwell. We live within the echo of an ancient collision, feeling its gentle sway without knowing it was there. Those same ancient collisions left behind more permanent traces. Long rivers of stars torn from devoured companions. The Radcliffe Wave is a transient memory, a disturbance that will eventually fade as gravity pulls the disk flat once more. But other scars from galactic encounters endure far longer. Every impact that bends the disk also strips stars from passing satellites. These orphaned stars do not fall back neatly. Instead, they continue orbiting the Milky Way on elongated paths, forming long, coherent streams that wrap around the galaxy multiple times. Some streams remain bound within the disk, phase-wrapped into subtle overdensities. Others escape the plane entirely, arcing high into the halo where friction is low and orbits preserve their shape for billions of years. Gaia's precise measurements have revealed dozens of such streams, ghostly rivers of stars with shared chemistry and motion, betraying common origins. Each tells a story of cannibalism, the Milky Way growing by devouring smaller galaxies over cosmic history. The disk remembers every blow it has taken, and some memories drift far beyond the plane as ghostly stellar streams. The Radcliffe Wave connects directly to this larger tale. The same satellite passages that excited the local oscillation likely contributed stars to nearby streams. Simulations show that Sagittarius's repeated plunges have scattered debris across the solar neighborhood and beyond. Other waves in the disk, smaller ripples discovered by Gaia, may trace more recent or distant impacts. As we map these structures, patterns emerge. The outer disk shows signs of widespread bending and flaring, consistent with multiple satellite encounters. Vertical motions are not random. They organize into large-scale modes, like vibrations on a vast membrane. The wave and the streams together reveal a galaxy still settling from its turbulent youth. Billions of years ago, the Milky Way was smaller, surrounded by a swarm of companions. Mergers built its mass and spin. Today, only the largest survivors, like the Magellanic Clouds, remain visible. The rest have been shredded, their stars blended into the halo and disk. Yet traces persist. Chemical signatures in stream stars differ subtly from native Milky Way populations, lower in heavy elements, frozen from an earlier epoch. Velocity patterns reveal the direction and timing of infall. Our quiet position near the Radcliffe crest may owe something to these dynamics. The wave's upward motion could have lifted the local gas, creating a temporary lull in star formation that allowed the sun to form in relative peace. The mysteries are intertwined, a local ripple, excited by ancient violence, surrounded by the permanent debris of that same violence. High above and below the disk, Gaia has revealed dozens of shredded galaxies now orbiting within our own. High above and below the disk, Gaia has revealed dozens of shredded galaxies now orbiting within our own. These are not intact companions like the Magellanic Clouds, still visible as faint smudges in southern skies. These are ghosts, long rivers of stars stretched into thin, coherent streams that wrap around the Milky Way multiple times. Each stream is a fossil of galactic cannibalism. Over billions of years, the Milky Way has grown by devouring smaller galaxies that ventured too close. Gravity tears them apart slowly, flinging their stars into elongated orbits, while dark matter and gas blend invisibly into the halo. Gaia's extraordinary precision, measuring positions and motions for billions of stars, has turned archaeology into revelation. Before 2018, only a handful of streams were known, traced painstakingly through chemistry or velocity. Now, dozens have emerged, each with distinct signatures of origin. The most dramatic is Gaia Sausage Enceladus, often shortened to GSE. Discovered in Gaia's second data release, it reveals a major merger roughly 8 to 10 billion years ago. A dwarf galaxy, perhaps 1/5 the Milky Way's mass at the time, plunged nearly head-on. Its stars scattered into highly eccentric orbits, elongated like sausages, hence the nickname. These stars dominate the inner halo today, their chaotic motions betraying the violence of impact. Chemical abundances show they formed earlier, in a system poorer in heavy elements than the young Milky Way. Another ancient merger left the Kraken, a name chosen for its many tangled streams, identified through combined Gaia and spectroscopic data around 2020 to 2021. It may represent one of the earliest known accretions, perhaps 11 billion years ago, when the Milky Way was still assembling its disk. Sequoia, also called Arjuna, appears as a more retrograde stream, stars orbiting opposite to the galaxy's spin. Its high energy suggests a dwarf galaxy captured on a backward path, shredded into a distant halo component. Smaller streams bear poetic names, Helmi streams from 1999 discoveries, now refined, Phlegethon, Iitoi, Nix, each tells of minor mergers, some as recent as a few billion years. Together, they map the Milky Way's growth like rings in an ancient tree. Our galaxy grew fat by devouring dozens of smaller companions, and their bones now orbit as detectable rivers of stars, stand beneath the halo on a dark night. The faint glow you perceive is not uniform. It contains these hidden currents, stars from long-dead galaxies drifting through our own. Their shared motions, preserved for billions of years in the low-friction halo, allow us to reconstruct the collisions that built everything we see. The process continues today. The Sagittarius stream, debris from the ongoing disruption of the Sagittarius dwarf, loops visibly around the sky. Gaia has traced its multiple wraps, showing how it is slowly dissolving into the halo. These streams are more than relics. They carry chemical fingerprints of their birthplaces, lower metallicity, different element ratios, helping us understand early galaxy formation across the universe. And their orbits reveal the shape of the dark matter halo itself, slightly flattened, slightly triaxial. Some streams plunge dangerously close to the black hole itself. Not all merger debris stays safely in the distant halo. Some streams dive deep into the galaxy, interacting with the bar, the bulge, and even the central black hole. The Gaia-Sausage-Enceladus merger was so energetic that many of its stars reach pericenters, closest approaches, within a few thousand light-years of the center. Their highly radial orbits carry them from vast halo distances inward at high speed, then fling them outward again. In phase space, the abstract map of position and velocity, these stars form distinctive plumes or shells, like ripples frozen in time. Other streams show signs of perturbation by the central bar. The bar's non-axisymmetric gravity acts like a mixer, scattering stars and wrapping streams into complex patterns. What appears as separate substructures in the halo may be the same stream viewed at different orbital phases, wrapped multiple times like ribbon around a maypole. Recent analyses through 2025 have identified streams that pass perilously close to Sagittarius A. One candidate, linked to the Sequoia or Kraken progenitor, includes stars on orbits that skim the inner few hundred light-years. Their survival implies the merger happened early enough that the black hole was less massive, or that dynamical friction has not yet dragged them fully inward. These inner passages leave subtle signatures. Hypervelocity stars, flung outward at enormous speeds, may originate from disruptions near the black hole, their trajectories tracing back to accreted streams. Chemical tagging reveals metal-poor stars in the bulge that do not match native populations, hinting at delivered material from shredded dwarfs. Phase space wrapping creates apparent substructures that puzzled astronomers for years. The splashes seen in Gaia data, over densities like the Hercules stream or anticenter structure, are now understood as wrapped remnants of major mergers. The disk itself bears scars. Vertical heating from ancient impacts thickened the old stellar population, while radial migrations blended accreted and in situ stars. A few torn galaxies fell all the way to the heart, leaving signatures we are only now deciphering. The central region, already crowded with native stars, hosts a surprising fraction of accreted material. Studies combining Gaia motions with spectroscopy from SDSS and LAMOST show that up to half the inner halo stars may come from Gaia-Enceladus alone. Their eccentric orbits carry them through the bulge repeatedly, depositing energy and gradually dissolving. This blending complicates everything we thought we knew about the center. The gamma-ray excess, the radio filaments, even the black holes feeding history, all may bear imprints of delivered gas and stars from past mergers. A burst of accretion billions of years ago could have fueled past activity, then cleared the surroundings, explaining today's relative quiet. The streams reveal a Milky Way that is not pristine but composite, built from stolen pieces, still settling into equilibrium. And within this ongoing digestion, the very closest orbits hold the strangest surprises. even closer to the black hole orbit objects that seem to defy categorization altogether. The stellar streams carry us from the distant halo to the galactic heart, where the most intimate mysteries await. Among the frantic stars near Sagittarius A, the S-cluster members whipping around at percentages of light speed, astronomers have spotted objects that behave strangely. Labeled simply G1, G2, and later G3 through G6, they appear as compact infrared sources on highly eccentric orbits, approaching within a few hundred astronomical units of the black hole at closest passage. Ordinary stars on such orbits should survive intact, but these objects stretch dramatically as tidal forces pull them, elongating into filamentary shapes before rounding out again on the far side. G2, observed closely during its 2013-2014 pericenter, brightened and lengthened, but did not disintegrate as some models predicted. Among the frantic stars near Sagittarius A, drift dusty imposters that stretch and survive where nothing should. The leading explanation casts them as gas clouds, perhaps remnants of disrupted protoplanetary disks or tidal debris from earlier encounters, enveloped in thick dust that shields them from immediate evaporation. Yet their compactness and repeated survival challenge this view. Some orbits have completed multiple passages without total destruction. An alternative proposes hidden binaries, pairs of stars merged within dusty envelopes, appearing single until tides reveal their nature. Recent infrared spectroscopy, with instruments like gravity on the Very Large Telescope, has tracked their motions with exquisite precision, showing orbital periods and shapes consistent with bound objects. As of early 2026, newer detections, G3 through G6, show similar behavior. Dusty, extended during approach, yet coherent enough to return. Their spectra reveal broad emission lines suggesting outflowing gas, but also hints of stellar features. These wanderers orbit in a crowded, hostile environment where radiation and tides should strip or destroy anything fragile. Their persistence raises questions about hidden reservoirs of gore near the black hole, or novel stellar evolution paths in extreme conditions. The G objects bridge scales, from galaxy-wide streams delivering material over billions of years, to intimate dances on human timescales. They may be the final stage of accretion, debris from ancient mergers finally reaching the center, or local phenomena born in the central chaos. These strange wanderers may be gas clouds masquerading as stars, or something entirely new. These strange wanderers may be gas clouds masquerading as stars, or something entirely new. Zoom in once more to the very doorstep of Sagittarius A, where gravity reaches its most extreme. Here, in the S-cluster, a handful of ordinary stars race along tight orbits, completing laps in mere decades or even years. But among them drift objects that do not behave like stars at all. The story begins with G1 and G2. G1 was discovered first in the early 2000s as a faint infrared source on a highly elongated orbit. Its path brought it within about 300 astronomical units of the black hole at closest approach, roughly the distance from the Sun to the asteroid belt beyond Mars. Observations in 2004-2005 caught it during pericenter, the moment of nearest passage. The object appeared compact then, but later images showed it slightly extended, as if gently stretched by tidal forces. G2 drew far more attention. Identified around 2011, its orbit was even tighter, predicted to skim just 200 astronomical units from the event horizon in 2013 to 2014. Many astronomers braced for drama. Pure gas clouds, some argued, would be torn apart completely, feeding the black hole in a brief flare of light. Others predicted only mild disruption. As G2 approached, telescopes around the world watched intently. Infrared instruments like those at the Very Large Telescope tracked its motion with unprecedented precision. In the months before pericenter, it began to lengthen, stretching into a thin filament along its orbital path. Brightness increased. Dust, heated by tidal compression, glowed more fiercely. Yet the expected fireworks never arrived. No dramatic accretion flare lit up Sagittarius A. The black hole remained quiet. After passage, G2 gradually recompressed. By 2015-2016, it had rounded out again, trailing a faint tail of disturbed material, but largely intact. Follow-up observations through the early 2020s showed it continuing its orbit, dimmer now, but recognizable. The pattern repeated with newer discoveries. G3 through G6 identified progressively from 2019 to 2024, using improved adaptive optics and instruments like Gravity and Osiris follow similar eccentric paths. Each approaches within a few hundred AU of the black hole, stretches noticeably during pericenter, brightens in certain wavelengths, then recovers on the outbound leg. G3 and G4 have already completed observed passages. G5 and G6 are approaching theirs in the coming years. All share common traits: compact when far out, dusty and extended near the black hole, surviving where simple models say they should not. Their masses, estimated from orbital dynamics, range from a few Earth masses to perhaps planetary scale, far too low for ordinary stars, yet too coherent for loose gas. Objects that approach the black hole too closely should be torn apart, yet some return intact, hiding their true nature. These events unfold on human timescales, decades between pericenters, offering a rare window into real-time galactic dynamics. Unlike distant mergers or ancient waves, the G-objects let us watch the black hole's influence directly, almost like a laboratory experiment at nature's most extreme scales. Their survival raises questions about hidden processes right at the event horizon's edge. Processes that might shield fragile objects or reveal entirely new ways matter endures tidal stress. The persistence of the G objects has sparked two main competing explanations, each with its own appeal and challenges. The first sees them as gas clouds, perhaps remnants of disrupted protoplanetary disks around young stars, or tidal debris from earlier close encounters. Thick dust cocoons would shield cooler gas inside from the intense radiation and winds near the black hole. During pericenter, tides stretch the envelope, heating dust and causing the observed brightening and elongation. After passage, Self-gravity or magnetic fields could pull the cloud back together. This pure cloud model fit early predictions for G2 well. Simulations showed a compact, dusty cloud could stretch without fully disrupting, matching the lack of strong accretion flare. Recent infrared spectroscopy supports it. Broad emission lines from hot gas, Br, gamma, and He. I features suggesting outflowing material, no clear stellar continuum. Yet the model struggles with longevity. Repeated passages should erode the clouds gradually. G1, observed over multiple orbits, remains surprisingly compact, far from pericenter. The newer objects show similar resilience. If they are loose gas, why do they not dissipate more quickly in the harsh environment? The alternative theory proposes something more structured. Merged binary stars hidden within dusty envelopes. Imagine two stars, locked in a tight orbit, spiraling together over time due to gravitational wave emission or interactions in the dense cluster. The merger produces a single bloated star surrounded by a thick shell of dust and gas ejected during the coalescence. From afar, it appears as a faint, dusty source, not a normal star, but not pure cloud either. During pericenter, tides stretch the dusty envelope dramatically, mimicking cloud behavior. The central merged star, however, remains bound, ensuring survival. After passage, the envelope settles back, ready for the next orbit. This binary merger scenario gained traction around 2018 to 2020, especially for G1, whose orbit aligns closely with G2's in a possible common plane. If both originated from the same disruptive event, perhaps a binary disrupted by the black hole long ago, their dusty remnants could explain the shared characteristics. Latest infrared spectroscopy, from Gravity and Symphony through 2025, adds nuance. Some objects show double-peaked line profiles, hinting at rotation or bipolar outflows, consistent with a central object driving winds. Others display more symmetric, cloud-like spectra. Hybrid models now emerge, young stellar objects with massive disks, or post-merger stars still shedding material. As of early 22R6, no single theory dominates. Upcoming pericenters for G5 and G6, combined with James Webb Space Telescope mid-infrared observations, promise finer spectral resolution. Polarimetry may reveal magnetic field structures holding clouds together. X-ray monitoring could catch subtle accretion if hidden stars feed the black hole quietly. Are the G-objects stars wearing disguises, or clouds that somehow hold together against impossible tides? Whatever their nature, they highlight how much activity persists near the black hole, despite its overall quiescence. They may represent a steady trickle of material, the final delivery from ancient streams or local stellar evolution, keeping the center from total starvation. While we watch these objects dance with the black hole, the larger halo hides even subtler shadows, shadows cast not by stars or gas, but by gravity itself. The G-objects, for all their drama, are visible players in a bright, crowded stage. Farther out, in the vast, faint halo, subtler disturbances hint at entirely invisible actors. cold dark matter theory predicts that the Milky Way's halo should swarm with thousands of smaller subhalos, clumps ranging from millions down to perhaps Earth masses, remnants of early structure formation. These subhalos would orbit quietly, too diffuse to form stars, detectable only through gravitational influence. Direct detection remains elusive, but indirect signs accumulate. Stellar streams, those rivers of accreted stars, should flow smoothly along their orbits. Yet Gaia has revealed gaps, kinks, and wobbles in several, most famously in GD1 and Palomar. 5. In GD1, a thin, cold stream, a clean gap appears on one side, matched by a spur of stars offset on the other, as if something massive brushed past, tugging stars aside. Similar perturbations mark other streams. Simulations show that dark subhalos of roughly 10 million solar masses passing nearby could produce exactly such features without visible counterparts. Beyond the visible streams, the galaxy may host thousands of invisible clumps that only betray themselves through gravity. These perturbations are rare. Only a handful of streams show clear signs, but that matches expectations. Most subhalos orbit far out or pass at safe distances. Denser, smaller clumps might create micro-lensing events or heat the disk subtly, but evidence remains tentative. The search intensifies with each Gaia release, and complementary surveys like DESI and Rubin Observatory precursors. Machine learning now scours phase space for faint overdensities or underdensities that could mark recent encounters. Theoretical models refine predictions, accounting for the Milky Way's actual merger history. The stakes extend beyond one galaxy. Finding, or firmly ruling out, substructure would test cold dark matter on small scales, where alternatives like warm or self-interacting dark matter make different predictions. A smooth halo would challenge the standard picture. Rich substructure would confirm it. The G-objects and streams connect here too. Ancient mergers delivered the visible debris we trace, but also the dark subhalos that accompanied them. Perturbations today may echo those same events, now stripped of stars. Gaia and future surveys hunt for gaps and wobbles that could reveal dark matter's hidden architecture. An architecture that might underlie every structure we have met, from waves in the disk to bubbles at the center. Gaia and future surveys hunt for gaps and wobbles that could reveal dark matter's hidden architecture. An architecture that might underlie every structure we have met, from waves in the disk to bubbles at the center. Step outward once more, beyond the bright disk and its rippling waves, beyond the shredded streams of visible stars, into the vast, faint halo that envelops everything. Here, gravity dominates almost alone. Stars are scarce, gas rarer still. What fills this enormous sphere is mostly dark matter, the invisible substance whose presence we infer only from its pull on the things we can see. In the standard picture of cosmic formation, dark matter is cold and collisionless. It clumps early, building a hierarchy of structures. Large galaxies like the Milky Way should sit within halos riddled with thousands of smaller subhalos, remnants of the first fragments that merged to form them. These subhalos range widely in mass, some as heavy as dwarf galaxies, others mere millions or even thousands of solar masses. Many should host visible satellites, the dwarf galaxies we do observe, roughly 50 around the Milky Way. But theory predicts far more. Hundreds of luminous dwarfs and thousands of dark ones, too small or disrupted to form stars. Yet we have found only a fraction of the expected satellites. This missing satellites problem has lingered for decades, eased somewhat by discoveries of ultra-faint dwarfs, but never fully resolved. The subhalos are there, the models insist, orbiting quietly, waiting to betray themselves through gravity alone. Direct detection remains beyond reach. Dark matter particles, if they exist as theorized, interact so weakly that they pass through ordinary matter unnoticed. But their clumps can tug on visible tracers, the thin stellar streams we traced earlier, or the smooth disk itself. Astronomers now hunt these invisible clumps by searching for disturbances. A subhalo passing through a stellar stream should leave a characteristic signature, a gap where stars were scattered away, or a density enhancement where orbits bunched. The effect is subtle, a slight offset in velocity or position, but Gaia's precision makes it detectable. Simulations guide the search. They show that subhalos of 10^7 to 10^9 solar masses, crossing streams at typical relative speeds, produce gaps tens of light years wide, with accompanying spurs of offset stars. Smaller clumps might heat the disk vertically or create tiny warps. Larger ones could explain some of the known dwarf disruptions. As of early 2026, the census continues. Rubin Observatory precursors and Gaia's final releases have expanded the sample of cold streams to dozens. Machine learning algorithms scour phase space for anomalies. Theoretical models refine predictions, incorporating the Milky Way's actual accretion history, the major mergers like Gaia and Enceladus that may have stripped or destroyed many subhalos. The Milky Way should be surrounded by thousands of dark satellites, yet we have detected only a fraction. This quiet hunt carries profound stakes. Rich substructure would bolster cold, dark matter. A smoother halo might favor alternatives, warmer particles, self-interactions, or even modifications to gravity. Every gap or wobble brings us closer to distinguishing these possibilities. The search is patient, methodical. Streams are fragile detectors, long, thin, and cold in velocity space. Their coherence makes even minor perturbations stand out against the background. Some gaps in streams suggest recent passages, encounters that happened mere hundreds of millions of years ago, fresh in cosmic terms. The most compelling evidence emerges from specific streams where disturbances match subhalo predictions almost eerily well. The clearest case remains GD1. This thin, ancient stream stretches across the northern sky, remarkably narrow and cold, stars sharing nearly identical motions. In 2018 to 2019, Gaia revealed a clean gap roughly 10 degrees long, with a spur of stars offset on one side. The geometry is striking, as if an unseen mass brushed past, pulling stars into a parallel track while thinning the main flow. Simulations show a sub-halo of about 1008 solar masses, passing at the right angle and speed, could produce exactly this pattern. No visible counterpart exists. No dwarf, no star cluster. The perturber, if real, is dark. Palomar. 5 offers another candidate. This globular cluster trails long tidal tails visible as streams. Gaia and follow-up imaging reveal underdensities and epicyclic overdensities along the tails, wiggles consistent with multiple subhalo encounters. Recent 2024 analyses identified a particularly sharp gap in the leading tail, matched by velocity shifts detectable in spectroscopy. Newer streams have added to the tally. The Orphan Chenab stream, a major halo structure possibly linked to a disrupted dwarf, shows subtle density variations along its length. A 2025 study using combined Gaia and DESI data flagged a potential gap spur pair, best fit by a 5 10^7 solar mass subhalo crossing roughly 500 million years ago. Other candidates emerged in 2024-2025. The Jhelum stream displays an offset branch that modeling attributes to a low-mass perturber. The Phoenix stream, faint but extended, harbors a density drop consistent with a recent encounter. Machine learning searches across the growing catalog flagged several more tentative features, faint kinks in lesser-known streams like Indus and Wilka Yaku. Not every anomaly proves a subhalo. Internal dynamics, cluster dissolution, bar resonances, or even past satellite interactions can mimic effects, but the best cases resist alternative explanations. Statistical analyses combining multiple streams suggest the observed perturbation rate aligns with cold dark matter expectations, assuming a standard subhalo mass function. A single missing segment in a stellar river might mark where an unseen dark clump passed by. These detections, though indirect, excite astronomers because they probe scales inaccessible to particle detectors or lensing surveys. A confirmed subhalo of 10^7 solar masses would rule out some warm dark matter models. Multiple low-mass perturbations could constrain self-interactions. The hunt accelerates. Upcoming Rubin Observatory full operations will map fainter streams and resolve finer structures. Pulsar timing arrays might catch disk crossings by nearby clumps. Even gravitational wave detectors could glimpse extreme low-mass subhalos through primordial backgrounds. The invisible clumps, if found in abundance, would complete the picture, a hierarchical halo underlying the visible galaxy, shaping its growth and dynamics from the outside in. Even denser hidden structures may lurk in vast molecular clouds. We are only now mapping fully reservoirs not of dark matter, but of the ordinary gas that will birth tomorrow's stars. The halo's dark substructure may be the most elusive architecture, but the galaxy hides other vast reserves closer to the plane. enormous filaments of cold molecular gas, only recently revealed in full. These are not the compact clouds of star-forming regions, but long, thread-like structures stretching hundreds or thousands of light years. Some run radially from the center outward, others coil along spiral arms. They contain millions to tens of millions of solar masses of raw material, enough to fuel entire generations of future stars. For years, individual bones were known. The Nessie filament, a dark infrared spine in the Scutum centaurus arm, the dragonfly or other bone-like threads. But systematic surveys have now connected them into a larger network. High-resolution CO mapping with telescopes like ALMA and APEX, combined with dust continuum from Herschel and Planck, revealed giant molecular filaments as a common feature. Some exceed 1,000 light-years in length, remarkably straight or gently curved, often bridging between arms or linking to the central zone. These structures sit in the interarm regions or along arm skeletons, positions where gas accumulates slowly, resisting immediate collapse. Magnetic fields, inferred from polarization, thread along their lengths, perhaps stabilizing them against fragmentation. Turbulence and shear from differential rotation keep them coherent yet quiescent. The galaxy still conceals enormous reservoirs of raw material for future generations of stars. Recent discoveries highlight hidden star-forming potential. Vast clouds, obscured by foreground dust, host embedded clusters only now detected in infrared or radio. Some filaments show chains of dense cores, prestellar seeds waiting for a trigger. Others remain almost pristine, with star formation efficiency orders of magnitude below dense arm clouds. These reservoirs may explain the Milky Way's steady, moderate star formation rate. Gas does not rain in chaotically, but collects in organized channels, released gradually. Past perturbations, satellite passages, bar dynamics, or density waves could have shaped their distribution. The filaments connect to earlier mysteries. Some align with the edges of Fermi bubbles or extend from the central molecular zone. Others parallel the Radcliffe wave, perhaps excited by the same impacts. Their mass rivals entire dwarf galaxies, yet they remain largely dormant. Mapping continues apace. New facilities like the Square Kilometre Array precursors trace fainter emission, revealing finer substructure. James Webb deep fields pierce dust to count embedded protostars. As of early 2026, the catalogue of giant filaments grows rapidly, reshaping models of galactic gas flow. These hidden reserves remind us that the Milky Way is not finished evolving. Much of its future lies locked in cold, patient clouds, awaiting the right compression or shock to ignite. Since 2024, new surveys have uncovered structures we never suspected, features that tie together the center's violence, the disk's ripples, and the halo's ghosts into a more dynamic whole. Since 2024, new surveys have uncovered structures we never suspected, features that tie together the center's violence, the disk's ripples, and the halo's ghosts into a more dynamic whole. The pace has only quickened. In 2023, 5 alone, fresh data streams arrived from multiple frontiers, each peeling away another thin layer of the galaxy's veil. Instruments long in operation delivered their deepest insights yet, while others began previewing capabilities that promise even greater clarity. Gaia, after completing its final observations in January 2025, entered the intensive processing phase for its fourth data release, expected later in 2026. Early previews and focused studies released throughout the year already hinted at riches to come. Refined proper motions revealed subtler phase-base substructures in the halo, faint overdensities suggesting previously unrecognized merger remnants. Vertical velocity maps of the disk sharpened the Radcliffe Wave's extensions, tracing its influence across multiple spiral arms. And in the inner galaxy, improved parallax distances uncovered hidden stellar associations near the bar ends, regions where gas funneling may drive episodic star formation. Meanwhile, the James Webb Space Telescope continued its penetrating gaze through dust. Deep mid-infrared fields of the galactic center, released in batches through 2025, exposed obscured features in unprecedented detail. Sagittarius C, a massive star-forming complex just 300 light-years from the black hole, emerged as a turbulent nursery packed with protostars, yet strangely inefficient, echoing the central molecular zone's inhibited collapse on smaller scales. New spectroscopy caught fleeting flares from Sagittarius A itself, brief brightenings suggesting infrequent accretion of small clouds or debris, perhaps linked to the G object's dusty passages. Further out, JWST mapped embedded clusters along giant molecular filaments, revealing chains of dense cores glowing faintly in cooled dust. These observations confirmed that much of the galaxy's raw material remains locked in quiescent reservoirs, awaiting triggers we are only beginning to understand. On the high-energy front, updated all-sky maps from Aerosita refined the Fermi bubble's X-ray counterparts. 2025 analyses showed sharper temperature gradients at the edges and detected faint extensions toward higher latitudes, suggesting the outflows may have pierced farther into the halo than previously measured. Embedded cold hydrogen clouds, mapped in finer detail with radio follow-ups, appeared more numerous, survivors of entrainment in the million-degree plasma, hinting at continuous replenishment from the disk. Low-frequency radio surveys delivered one of the year's most visually striking advances. In late 2025, a consortium using the Murchison Wide Field Array and other precursors assembled the largest color composite radio image of the Milky Way ever produced, a panoramic view spanning multiple wavelengths that highlighted vast synchrotron loops, supernova remnants, and magnetic structures invisible in optical light. The image traced polarized emission along the galactic plane, outlining organized field lines that thread through spiral arms and connect to halo outflows. Meerkat and other SKA pathfinders contributed high-resolution snapshots of the central filaments, resolving helical twists and faint connections to molecular outflows. These previews of the full square-kilometer array's power revealed substructure within threads previously seen as smooth. Every year, new instruments peel away another thin layer. And 2025 brought surprises no model predicted. A colossal wave spanning tens of thousands of light years, hinted in earlier Gaia releases, gained clearer amplitude and coherence. Faint radio arcs high above the plane suggested relic outflows older than the Fermi bubbles. And in the halo, tentative gaps in newly catalogued streams aligned suspiciously with dark sub-halo predictions. These revelations did not arrive in isolation. They built on one another, cross-calibrated across wavelengths, painting a galaxy more interconnected and more restless than recent pictures suggested. These fresh revelations only sharpen the older questions, forcing us to revisit structures we thought we understood. The new data from 2025 did not simply add details. It reshaped interpretations of mysteries we have carried through this journey. The Fermi bubbles, long dated to a few million years ago, now appear more complex in light of E Rosita refinements. Sharper edges and embedded cold clouds suggest multiple episodes, perhaps an older, larger outflow overlaid by the gamma-ray bright phase. The high-latitude extensions imply greater energy release, tilting models toward sustained black hole feedback rather than a single explosive event. Yet the symmetry remains almost too perfect, keeping stellar wind scenarios alive. The galactic center gamma-ray excess felt the impact most directly. Improved background subtraction in late 2025 Fermi analyses, combined with JWST's census of faint infrared sources, resolved more millisecond pulsar candidates in the inner bulge. The excess's morphology sharpened, slightly less bulbous, with extensions tracing the bar's influence. The balance shifted further toward pulsars, though a residual spherical component left room for a subdominant dark matter signal. The debate grew more nuanced. Perhaps both contribute, with merger-delivered stars boosting the pulsar population. Stellar streams gained new branches and perturbations. Gaia's final focused releases clarified phase wrapping in major mergers like Gaia Enceladus, revealing wrapped substructures that mimicked independent accretions. The Radcliffe Waves extensions, traced farther along the Perseus and Scutum arms, suggested it connects to broader disk oscillations, perhaps a standing mode excited by multiple satellite passages rather than one event. The radio filaments benefited from Meerkat's resolution. Helical fields and connections to outflows hinted at transport mechanisms, magnetic launching from the disk, perhaps carrying energy into the bubbles. The low-frequency panoramic image outlined larger loops encompassing the central zone, suggesting the visible threads are bright tips of a galaxy-wide magnetic skeleton. Even the G objects evolved in understanding. JWST mid-infrared monitoring caught spectral changes during recent approaches, showing broader dust features consistent with evaporating envelopes around merged binaries. The flares from Sagittarius I coincided loosely with predicted pericenters, hinting at tidal stripping feeding the black hole quietly. Structures we thought stable are now seen evolving in cosmic fast-forward. The giant molecular filaments, mapped more extensively, showed alignments with wave crests and stream infall directions, as if past perturbations organized the gas reservoirs. Dark sub-halo candidates gained statistical weight, Multiple gaps across streams, aligned better with predictions when incorporating the updated merger history. Taken together, 2025's advances portrayed a galaxy in continuous flux. Ancient mergers' echoes overlap with recent central activity. Outflows shape the halo, while disk waves respond to the same forces. The Milky Way breathes on multiple timescales: million-year outbursts, 100-million-year oscillations, billion-year assembly, all layered atop one another. Older questions sharpened rather than resolved. The black hole's past activity seems more episodic, its current quiet more precarious. Dark matter's signature grows fainter in direct signals, but stronger in gravitational hints. The disk's hidden reserves appear poised, waiting for the next disturbance. The picture grows richer, more interconnected. Yet the deepest shadows remain, demanding tools not yet fully online. Yet many secrets will remain sealed until the next generation of observatories comes online. Instruments that will map the galaxy with breadth and depth we can scarcely imagine today. The revelations of 2025 whet appetite rather than satisfy it. Many structures, faint streams, subtle perturbations, obscured cores, hover at the edge of detectability, their full stories locked behind current limits. Within the coming decade, a new wave of observatories promises to illuminate the hidden skeleton almost completely. The Nancy Grace Roman Space Telescope, slated for launch as early as late 2026 or 2027, will conduct wide-field infrared surveys of the galactic plane and bulge. Its micro-lensing campaign alone will probe billions of stars for subtle wobbles, revealing hidden populations, from free-floating planets to faint halo members. Deep bulge fields will census obscured stars, clarifying accreted versus native fractions and refining bar dynamics. The Vera C. Rubin Observatory, beginning full operations around 2026-2027, will transform time-domain astronomy from the ground. Its legacy survey of space and time will image the southern sky repeatedly, catching transients across the disk and halo. Stellar variability and proper motions, combined with spectroscopy, will trace streams in unprecedented detail and hunt subhalo perturbations in real time. The full square kilometer array, with phases coming online through the late 2020s and 2030s, will revolutionize radio views. SKA Low in Australia will map hydrogen across cosmic time, while detailing faint synchrotron structures in the halo. SKA Mid in South Africa will resolve pulsar populations in the center, potentially resolving the gamma ray excess definitively, and trace magnetic fields galaxy-wide with polarization precision orders of magnitude beyond current capabilities. Ground-based extremely large telescopes, the European ELT 30-meter telescope and Giant Magellan telescope, will bring spectroscopic power to bear. Adaptive optics and multi-object spectrographs will dissect individual stars in crowded fields, measuring abundances in halo streams to fingerprint progenitors, or velocities near the black hole to track G-object orbits and test general relativity further. Future X-ray missions, successors to Rosita and Chandra, may map hot halo gas and bubble evolution with greater sensitivity. Next-generation gamma-ray observatories like the Cherenkov Telescope Array will probe the excess spectrum at higher energies, distinguishing particle annihilation from pulsar emission. Within a decade, we may finally see the full hidden skeleton of the Milky Way. These tools will overlap and complement one another. Roman's infrared census paired with Rubin's optical transients, SKR's radio continuity with ELT spectroscopy. Multi-messenger views, gravitational waves from LISA detecting intermediate black holes in streams, or neutrino signals hinting at dark matter processes. The result could be transformative, a near-complete dynamical map from central filaments to outer halo substructure. Ages and origins of mergers precisely dated. Feedback cycles quantified. Dark matter's small-scale nature tested rigorously. We may witness the next G-object disruption or black hole flare in exquisite detail. Trace the Radcliffe waves' slow damping or excitation by new passages. Catalog thousands of giant filaments and their star-forming potential. The galaxy's breathing will become visible. Its slow inhale of gas, outbursts of energy, settling of ancient scars. Hopeful anticipation rises naturally. For the first time, we stand on the threshold of seeing our home, not as fragments, but as a coherent, living whole. But even with perfect vision, some questions may remain forever open. Whispers of the universe's deepest nature that no telescope can fully silence. As we await these future eyes, the river of light overhead continues its patient watch, containing all these hidden layers, all these emerging shadows, still guarding a few irrevocable secrets at its heart. But even with perfect vision, some questions may remain forever open. Whispers of the universe's deepest nature that no telescope can fully silence. We have traveled far together, from the veiled river of light overhead, through the quiet monster at the heart, past colossal bubbles and rigid threads, across undulating waves and ghostly rivers of stolen stars, into the intimate masquerade near the event horizon, and the invisible clumps that tug silently from the shadows. We have lingered over vast reservoirs of cold gas and the fresh shadows revealed in recent years. Each structure, each mystery, appeared at first as an isolated puzzle. Yet, as we step back, connections emerge, subtle threads binding them into a single, ongoing story. The Fermi bubbles rise from the center, perhaps exhaled by the black hole during a past feast, or driven by a burst of central star formation. Their energy reshapes the halo, while cold clouds survive within, hinting at continuous exchange with the disk. The radiofilaments stand nearby, channeling magnetic forces that may help launch those outflows. The gamma-ray excess glows softly in the same region, perhaps the combined whisper of thousands of ancient pulsars, perhaps a faint echo of dark matter itself. Closer to home, The Radcliffe wave ripples through our neighborhood, excited long ago by a satellite passage whose debris now drifts as stellar streams in the halo. Those same ancient mergers delivered the material that thickened the disk, warped its layers, and scattered subhalos whose gravity still perturbs streams today. The giant molecular filaments collect the gas that falls back slowly, organizing reservoirs for future stars while tracing the scars of past disturbances. The G-objects dance at the very edge of the black hole's grasp, perhaps the final fragments of those long-ago disruptions, dusty remnants reaching the center after billions of years. Their survival, like the black hole's current quiet, speaks of delicate balances, feedback that clears surroundings, tides that stretch but do not always destroy. Recent discoveries tie these threads tighter. Sharper maps show bubbles with multiple layers, waves extending across arms, streams wrapped by the bar's gravity. Magnetic skeletons outline the plane, connecting filaments to larger loops. Hidden clouds and subhalo gaps remind us that much remains unseen, patiently waiting. Every mystery we have met is a reminder. We live inside a living, breathing giant, still growing and remembering its past. The Milky Way is not a static portrait, but a dynamic biography. It records its youth in the halo's ancient streams, its maturity in the disk's layered memories, its recent breaths in bubbles and waves. Violent mergers built its mass, quieter accretion feeds it still. Outbursts clear the center, inhibition preserves gas for tomorrow. Magnetism organizes chaos. Dark matter provides the unseen scaffold. No structure stands alone. The black hole's past activity may have launched waves outward and excited oscillations we feel locally. Satellite passages that bent the disk also delivered stars and dark clumps whose influence lingers. Feedback from the center shapes the halo. Infall from the halo reshapes the center. We inhabit a galaxy in equilibrium, yet far from finished, evolving on timescales from human decades to cosmic epochs, all superimposed. Some hidden structures may point beyond the Milky Way itself, to questions of how typical our home truly is among the billions of spirals scattered across the universe. The interconnected structures we have explored do more than map our galaxy. They offer glimpses into larger cosmic truths. Consider the supermassive black hole's remarkable quiet. In many galaxies, similar beasts blaze as active nuclei, consuming gas voraciously and driving galaxy-wide winds. Our Sagittarius A flickers only occasionally, underfed despite surrounding reserves. This quiescence may owe to past feedback, outbursts like those inflating the Fermi bubbles clearing the inner regions, or inhibition in the central molecular zone, starving accretion. Comparisons with other galaxies suggest such calm phases are common in mature spirals. But the Milky Way's extreme symmetry and low activity place it toward the quieter end. If feedback universally regulates black hole growth, our structures provide a nearby laboratory. The bubbles, filaments, and possible past flares illustrate mechanisms that quench star formation and expel gas in more violent systems. Understanding their timing and energy refines models of how galaxies transition from starburst youth to settled middle age. Dark matter's nature hangs in similar balance. The gamma-ray excess, now leaning toward pulsars, yet retaining a stubborn spherical hint, probes particle properties directly. Subhalo perturbations in streams test the cold, collisionless paradigm on small scales. A rich population would confirm hierarchical formation. Scarcity or smoothness might favor alternatives. The Milky Way's detailed map, streams, waves, halo shape, constrains the gravitational potential uniquely, revealing whether dark matter clumps as expected or interacts in unexpected ways. The abundance of accreted material, Gaia Enceladus dominating the inner halo, multiple streams wrapping the disk, paints our galaxy as a typical cannibal. Most large spirals bear similar merger scars, yet the preservation of thin streams and coherent waves suggests relatively recent calm, perhaps after a turbulent youth. Our position in a quiet inter-arm region, cradled by the Radcliffe swell, may be unusually stable, shielding complex chemistry and biology from frequent disruption. The vast molecular reservoirs, organized yet inhibited, imply a moderate star formation pace that has persisted for billions of years. In more active galaxies, gas collapses rapidly. In starved ones, it dwindles. The Milky Way's balance has allowed steady enrichment of heavy elements without exhausting supplies, conditions perhaps favorable for planets and life. Our galaxy's secrets could reveal whether our quiet existence is typical or extraordinarily lucky. These implications ripple outward. A typical quiet center suggests many galaxies host dormant monsters, their past activity shaping habitability. Rich substructure supports the standard cosmological model. Anomalies might demand revision. The prevalence of waves and streams indicates ongoing minor mergers across the universe, keeping disks dynamic long after major assembly. Philosophically, the unfinished map humbles us. We see patterns of growth, regulation, memory, echoes of processes that built not just one galaxy but the cosmic web itself. Our home remembers its violent past, yet maintains fragile equilibrium, allowing fragile life to emerge and ponder. The structures whisper that stability is temporary, achieved through cycles of disturbance and recovery. They remind us we are transient guests within a far older, patient story. The final question is not what we have found, but what we may never fully know, no matter how sharply we see. As our journey ends, let us return once more to where it began, a quiet night beneath the stars. Step outside, far from lights, and look up. The faint river of the Milky Way stretches overhead, unchanged to your eyes from the view of ancient sky watchers. Yet now you know what lies within. Behind that pale band breathes the barred spiral, its arms sweeping gas into nurseries. At the heart waits the quiet black hole, surrounded by threads and clouds, occasionally exhaling vast bubbles that reach halfway to the edge. Waves undulate gently through the disk, carrying our sun on their slow rise and fall. Ghostly streams drift in the halo, memories of devoured companions. Invisible clumps tug silently, while enormous filaments hoard gas for stars unborn. Recent maps sharpen the picture. Future telescopes will sharpen it further. We may soon trace every major stream, resolve the excess's source, watch the next G-object dance, count subhalos by their gaps. The skeleton will grow clearer, the biography richer. Yet some shadows will endure. The exact trigger of ancient waves may remain ambiguous, multiple candidates overlapping in time. The gamma excess might resolve to pulsars with a faint dark matter whisper too subtle to isolate. The black hole's deepest past, its seed origin, its quiet phases, lies beyond direct record. Dark matter's particle nature, if not local, may demand signals from rarer events. Even with perfect vision, the galaxy's earliest moments blend into the universe's first light. Some processes operate on scales too vast, or timescales too slow for complete capture. Chance discoveries, an unexpected flare, a new perturbation, will continue, reminding us the story is never closed. The Milky Way has guarded its deepest structures for billions of years, and it may keep some forever. Stand beneath the river of light, feel small against its immensity, yet connected to its slow breathing. The dust that once veiled everything now feels less like obstruction and more like protection. A gentle haze preserving mystery in an age of revelation. Humanity's gaze has pierced farther than ever before, yet wonder remains. Each peeled layer reveals not final answers but deeper questions, pulling us onward. The map is unfinished, as all true maps must be. The galaxy continues its patient turning, remembering, growing, and we, brief sparks within its disk, continue watching, awed, curious, forever drawn to the light that hides so much yet shares just enough. The answers may not arrive all at once, but the act of wondering changes us. If tonight's journey stirred something in you, let it settle gently. Thank you for listening. This has been the calm unknown. Rest well and keep wondering.